Hello everyone, and welcome to our presentation on vehicle and object detection using Python, OpenCV, and TensorFlow. My name is Andrew Noseworthy, and Brady Walsh and I will be presenting you the slideshow prepared to summarize this project today. The purpose of this project was to explore the capabilities of moving object detection in video applications. Vehicles, objects, and people can all be detected, identified, and tracked through a video so long as they remain visible in the captured frames. Our implementation was coded in Python, and we used a YOLO v4 classifier with pre-trained weights capable of classifying over 80 different objects. OpenCV was used for video capture, while the open source machine learning platform TensorFlow was used to process the incoming video and match moving objects to the classes present in the YOLO v4 classifier. The setup of this code was arguably the most difficult aspect of this project. Neither team member had a deep knowledge of Python or any of the other tools used for this process, so getting set up for the first time was difficult. Firstly, we had issues using Python 3.9, so we converted instead to version 3.8 so we could gain proper support of the OpenCV and TensorFlow libraries. TensorFlow and OpenCV then needed to be installed. We used the package management software pip to accomplish this task. Next, the YOLO v4 weights were converted to a .pb file so they could be used with TensorFlow. There are a couple different ways to do this, but we accomplished it using the official method posted on PyPy. Finally, both OpenCV and TensorFlow needed to be initialized or included into the code. This was done using number sign include and by adding the file location to the system path, which allows the two softwares to be referenced.
Our finished code works as follows. The YOLO v4 weights are assigned to a variable and loaded with TensorFlow. OpenCV is then used to open a video and determine its FPS and size. An output destination for the processed video is then declared, and then, using a while loop, the code begins to cycle through the frames of the video one at a time. As it goes, it resizes the frames to 416 by 416, which is the standard size for YOLO, and uses TensorFlow to find valid object detections in the frame. Before moving on to the next frame, the detected objects are thresholded, so only the ones that have over a 50% confidence level are considered. After identifying and labeling the found objects, the while loop saves the frames to the output video and moves on to the next frame. 4 functions were created for this project and used in conjunction with a bit of other code. They are mainly what gets the system to work. Firstly, there is read class names. This function reads and returns the name of the classes detected in a given frame of the video. Item counter counts the number of objects detected at a given time. Format boxes sets the size of the bounding box around detected objects to the appropriate size, and drop bound box draws boxes and prints the relevant information for objects that have a weight over a specified threshold of 50%. We will now show you a demo of our code in action.
This is our code. It was coded in Python using Visual Studio Code, and it largely consists of the 2 files you see before you. While I'm talking, I'm going to go ahead and click play so that this can initialize and we can watch the video later on, as it takes a while to set up. Throughout this code, it's largely as stated in the presentation previously. This is the line to get our weights. This is where our weights are loaded. This is the source video location and the output video location line. This while loop is responsible for cycling through the frames of the source video and drawing the boxes. This code right here is responsible for detecting the objects and using TensorFlow and thresholding them. Right down here, this is resizing the boxes and placing additional information on the screen. And this here closes everything once it is done executing. Setup functions is used as a configuration file. It houses the functions as well as loads the YOLO classifier. as you can see, the code has begun executing on the bottom, and relevant information about objects being found in the video is being displayed. And also, this window here is now available to view of the video processing in action. You can see frame by frame each object that is being detected by the software, and in the top left you can see the counter working, and we have it set right now to be individually counting each different class of objects at once. So I'll let this run through, and then I will show you the finished version. Alright, the code is now done, and you can see that it outputs done and where the file has been saved to in the console. If we want to take a quick look at the information that was being printed out during that, we can. So it prints out the number of objects that were detected and what class they were, but it also prints out the location and name of each individual object that was found, as well as its confidence level. Here is the file that the video was saved to, and you can see that we have several videos in here already, but if we want to watch the one that we just processed, we can. And as you can see, the clip itself is actually only a couple seconds long. It's an important thing to note that in our code we don't use our graphics card, which would be possible to speed up the entire process. But because we only rely on our CPU, the entire process of analyzing that 1 10-second clip takes about 3 or 4 minutes, which is a rather long time.
Here are 2 screen captures of 2 successfully processed videos using our code. By using the OpenCV library, in addition to TensorFlow AI and the pre-trained weights of the YOLO v4 database, we were able to successfully label the objects of interest in video files. In addition to the identification, the code also displays the confidence of the detection, as well as the number of objects in each identifiable class on screen at one time. Here, in example 1, you can see the numerous people and bicycles labeled over each object and the tally counter of each in the top left corner. It has successfully counted the number of people and bicycles in the video frame. If you look at example 2, a similar object identification has been conducted, and this time the object detector is counting the number of cars in the video frame. As seen in the video, the tally counter has successfully counted the 4 cars in the video frame.
This slide displays a list of references used throughout the project to help our implementation of object and vehicle detection in video. Here are some more references that we used throughout the project for the same reason. So thank you to the people who came out today to view our presentation, and this would be the time for any questions the audience may have.